On lecture 37, we seriously start our discussion on the scientific elements of FEM. We are not interested on engineering application of FEM. There are many such specialized courses where you could do that, but we try to find out how the accuracy aspect of FEM is in the course of this lecture and the following lectures. We notice that the scientific element of FEM is in an effort to reduce the residue, not exactly, but in a weighted manner, and we talk about various variations of this method in terms of boundary and interior methods. We also talk about various versions of weighted residual methods. They could be a collocation method, or we could apply it at a subdomain, or one could actually employ a least square approach, or one could take the classical Bubnov-Galerkin method. The Bubnov-Galerkin method is a non-dissipative method, and which is quite interesting in its own right. So, we talk about this Bubnov-Galerkin method. In appearance, this Bubnov-Galerkin method appears to be as if we have separated the variables, but it is indeed not so. We will highlight why it is so. We also identify that the Bubnov-Galerkin method would be sort of non-dissipative. So, it can suffer numerical instability, and in the Bubnov-Galerkin method we choose the basis function itself as the interpolating functions, which are low order polynomials, but there are other ways of circumventing problems of Bubnov-Galerkin method. One of the method is the Petrov-Galerkin method, and its versions that we talk about here is the streamline upwind Petrov-Galerkin method of Hughes and the flow control FCBI method of Bathe and his colleagues. We basically having introduced all this, briefly get into the finite element approximation, talk about the various basis functions, and we notice that these basis functions could be local or global, and with this we will conclude this lecture. And touching upon the last topic, it is on finite element method, but I am not going to cover finite element method the way you will find in many books or in many other courses. I will focus upon the scientific element of it. So, we are going to highlight how FEM is similar or dissimilar with other methods. For example, say we did talk about a lot on finite difference methods throughout this semester. By and large, finite difference methods are quite good in terms of resolving scales with very high accuracy. One of the disadvantages of the finite difference methods that we have seen is it is little difficult to handle complex geometries. Okay. On the other hand, if you look at the other methods, those are available, for example, finite element or finite volume method, they are considered attractive because they are able to handle complex geometries, and therefore, they can take care of complicated boundary conditions too. Now, if that is so, we need to really find out if this methods, finite element and finite volume methods, also satisfy those nice properties which FDM gives automatically. I mean, not automatically, you will have to look for it and devise better methods. Keeping our point of view focused on FEM, essential idea, the big picture is that you have a computational domain, you split that computational domain into small subdomains, and you try to satisfy this governing equations in these subdomains in a piecemeal approach. Okay. And how do you satisfy the governing equation? That is also equally important. You just do not simply just plug it into the governing equation and say, well, it is satisfied. No, there are certain developed methodologies from calculus of variation, or what we are going to talk about is a little bit on weighted residual method. So, what we are saying that in FEM we will assume a form of the solution, which we will call as the trial solution or approximating functions, and then we will plug it into the differential equation, and then we will see that the differential equation will not be exactly satisfied. We, having done those error analysis, we are quite familiar that even with our best intention we are left with some errors to handle. At the equation level, that is what we call as the residue, and in FEM we try to reduce this residue, not exactly, it is impossible. So, you do it in some kind of a mathematical sense, which is given by this weighted residual method. So, we will talk about that. One of the things that distinguishes FEM and this class of FEM, FVM and FDM versus let us say spectral method is the solution method itself. Okay. What we saw that if we are looking for a solution, then we actually start off with some kind of approximation. That is our goal. So, approximate solutions can be actually broadly classified into two distinct categories. One is the global solution, another is a local solution. What do we mean by global solution and what do you mean by local solution? Suppose I have a function f of x and I write it like this. Then what you notice that we are writing the solution in terms of functions whose space dependence is given by this. This is a kind of an approximation. We are talking about approximation, right? So, this is one set of approximation where space dependence is given, let us say, by the Fourier series. Now, what you then try to do is you try to find out what this amplitudes of this Fourier series are by plugging this expression into a differential equation, and you get equations for f of k, and that is the method. Now, if I get a solution with say j equal to some 1 to n, and then I decide to add one more term, then what happens is, what about this function? If my domain is like this, let us say my domain is like this, it starts off from here and goes on till here. Now, if I keep changing this function here little bit, instead of kj I change it to say kj plus dk, a small change, then what will happen is that effect will be felt all over the domain. So, that is what is a global method is. So, a change in the approximate solution has a global effect across the domain. That is what we mean by global. So, one of the simplest example of this is the spectral method, Fourier spectral method. That is what we wrote here. Now, there are plus points and there are minus points. The plus point is when you apply global methods, then you could take fewer terms and get very accurate solutions. So, for example, if I am trying to solve an equation, differential equation of f, and then I may take 16 terms or 20 terms, and I find that is going to give me a pretty good solution. So, global method, one of the strongest point is that you can get by with taking far fewer number of points. That is good. But what happens is, if you make a change in this global solution components, any one of them, its effect is also global. Okay? So, that is one of the issue. In contrast, if what you could do is, you could keep solving the problem in a local sense. I could identify a subdomain and develop a method, apply it there, and then I try to solve it. And there, if I make some change here, the effect is kind of a local effect. It is not going to be percolated there. In fact, having done this finite difference method in such great detail over this semester, now you have realized that when we did those explicit spatial discretizations, they are like a local method, whereas the compact schemes which we did, they are like global method, because there each and every node were connected by those auxiliary equations that we wrote for those derivatives, right. So you can see that even talking about in these generalities within each method itself, we could distinguish between global and local methods. Okay, so that's what we are saying here, that in FEM we'll decompose the problem into smaller subdomains and try to satisfy governing equations in a weighted by some weighted residual method. And one of the essential element of FEM is these approximate solutions that we are writing, they are going to be simpler polynomials. Here it was like a cosine or sine function, which is a global function, but in FEM I would probably approximate the solution in this, and I could probably say, look, if this is one node and that is another node, my local solution behavior would be like this, a decomposition of two modes. Okay, this plus that, we'll see. So this is something, if I take say linear basis functions for this FEM, I would probably do that. So that is what we are saying here, that we'll take it as simpler polynomial. So I'm just showing the lowest order polynomial that's possible is the linear variation, right. Well, so you see, this is the sum and substance, that FEM is a local representation which is distinct from global methods like spectral method. Now, what are these weighted residual methods that we are talking about? Take a look at equation 1. It is your a generic problem where you probably do some kind of spatial discretizations and you end up with some kind of evolution equation like the one that is given in equation 1. You define it in the domain x in omega, and you also define the initial conditions and the boundary conditions as given in 2 and 3. Now, how do you develop this weighted residual method? You have to select a trial function, which we will call as u of n. U of n will have two parts. Okay, the first part relates to a space-time dependence of the problem, where this uj of x is the specific qualitative dependence that we are going to prescribe. That, as I told you, like if I look at a domain and if I say my uj of x is like this, so this two together, I could say that, look, this is my uj of x. Okay, so I prescribe that space dependence there. In addition, this in equation 4, this last part ub of x2 is put in there. That actually helps you in satisfying the boundary condition. So what you are trying to do is, one part of the trial solution is geared towards satisfying the differential equation, another part is geared towards satisfying the boundary condition, right. Well, I said that it is geared towards satisfying the differential equation. That is not necessarily guaranteed, because we are not specifying what this Cj of t is. So the time dependence is kept as it is. We do not know a priori what it is, but space dependence we are making some kind of a local guess. This is like what we did in our explicit method. We locally fitted a polynomial, right. So that is like fixing your uj of x. If I take a second order central difference scheme, then basically I am prescribing this uj of x is a kind of a quadratic polynomial. Okay, so that's the way we do. However, here what you are doing is almost like your separation of variable, right. There is a space dependence part segregated from the time dependence part. However, I would not explain it to you right away, but please do make note of the following fact, that the time dependence path, if it is truly time dependent and not space dependent, than what this subscript j is doing there. This is often not very clearly explained. We will come back to it later, but please pay attention to this. It is just not simply separation of variable the way we understand. If it was a pure separation of variable, I would not identify this C of t with individual nodes. There is an implicit space dependence also built in there, right? So this is something we will come back to it. In fact, I fail to see in most of books on finite elements where this part is highlighted, but that is one of the strongest point of FEM, which people have not sort of really highlighted. Okay. Now, what do? We prescribe a trial function u of n given by 4 such that the second part of 4 automatically takes care of the boundary condition, and then we try to classify in a sort of a rudimentary way all this collection of methods which we can use, where actually we satisfy the boundary condition explicitly by the choice of those u of b, then we call those methods are the interior methods. In contrast, you can also have boundary methods where the trial solution is chosen in such a way that it tries to satisfy the initial conditions and governing equations as accurately as possible, but does not satisfy the boundary condition. Okay. So boundary methods do not satisfy boundary conditions, and interior methods satisfy the boundary condition. This is the essential difference. The third category could be a mixture of the two, where the trial solution need not satisfy either the differential equation or the boundary condition. Now, even if I decide to choose the trial solution in such a way that okay, my intention is to satisfy the differential equation, and then I plug it into the differential equation as given in the right hand side of 6 here. Now, what you would be noticing that even with your best intention, that quantity will not be equal to 0, and that is your residue or the solution error that we talked about. So our equation is basically residue of the equation as obtained with respect to the trial solution that we have chosen. Now we can actually plug the same expression for our initial condition, and you would be even surprised that that also may not be satisfied even with the interior method. So that's why I said that's a kind of a artificial way of classifying methods, because even with your best intention, you will find this residues are not going to be equal to 0. Okay. So that is something we need to keep ourselves cognizant about it. So we should be careful about it. Now, we did not say anything about what this Cj of t is going to be. So what we are going to do is we are trying to find this quantity Cj of t by looking at the residue. And looking at the residue is not only going to be just looking at it, you have to basically minimize this residue in some sense. Okay, we need to minimize this residue to some negligible value in some sense, and then we try to find out what this function Cj of t are. Okay. One of the way of finding these functions Cj of t is to select some kind of a weight functions. Well, the weighted residual method, the sobriquet itself tells you that we are going to talk about some weights. Okay, that's what we are going to do. Let those weighting functions be Wj. Okay, and how many C of j we have? Well, I mean, as you have seen, we have taken n number of such functions in 4. So what we need to do is we need to derive equations for n number of such equations for evaluating n of these Cj's. Okay. So we will choose, first step is some weighting functions. What they are, we are going to talk about it shortly, n of them, and then we define a sort of a norm. Okay, some kind of a norm of a function v with respect to these weights. which will be defining by this, separated by a comma within a bracket, and that is nothing but actually trying to evaluate that quantity over the whole domain with the weight functions multiplied. So that's what we are going to do. Once we define this norm, then we would like to minimize the equation residual with respect to these weights. That's what this equation 9 is. That is the cardinal principle on which we will be working on this weighted residual method. So we will basically reduce this equation residue with respect to each and every one of these weight functions Wj. Well, whenever you have such a norm equal to 0, that means what? That means that these weights Wj's are orthogonal to this solution residue. That's the mathematical definition of orthogonality, right? If I have two functions, if they are orthogonal to each other, I can take a product of it and integrate over the whole domain. If they are not correlated, the integral should turn out to be 0, right? Correlation means non-orthogonality. Orthogonality means non-correlation. If two functions are not correlated, the integral of the whole thing should be equal to 0, right? So here also we are trying to say that, look, I will choose my trial solution in such a way that the residue of the equation that I would get should be orthogonal to some particular choice of Wj's. Okay, that's what the second point implies here. Now, if my original problem was time independent, then you could notice that we would not be taking C of j as a function of t. That will be a pure constant. In a time independent problem, we will just simply write Cj of t times Uj of x. Okay, and in such a case, equation 9 would give you what? Some kind of a algebraic relation for the Cj's, depending on the type of equation that we have, but that they will still be linear algebraic equations, right, for Cj's. Whereas if you have a complete space-time dependent problem, then the Cj's will be, of course, a function of time, and since you have already prescribed the x dependence and put it into the differential equation and evaluated the residue and then perform this integral with respect to Wj. Wj's are also functions of x. They are also space dependent functions. So, and you are integrating over the whole domain. So, space dependence part is integrated away. What remains is only the time dependence. So, that is what we are saying, that for the space time dependent problem, equation 9 would essentially give you some kind of a ordinary differential equation for this coefficient function Cj of t. Okay. So, that is the essential difference between time independent and time dependent problem. In one case, you will get a linear algebraic equation, in the other case, you will get a coupled ODEs. Now, if you have a space time dependent problem, so you are going to have ODE for the Cj's, right. So, you would require initial condition for those equations that you get it from your initial residue that we have already defined, right. We have shown here in equation 7 what the initial residue is. So, from here I could get some relationship for Cj at t equal to 0. So, that is the essential idea of using that initial residue as well. Now, as I told you that we will have a whole range of weighted residual methods, each one will differ from the other by the type of choice that we exercise in picking up these Wj's. Okay, we'll talk about it shortly. Okay. However, we must note this after all this thing, the trial solutions would not satisfy the governing equations exactly, even for the boundary method, and that's why we are getting this R of Eq is non-zero, right. So, let's now move over and look at some of the generic classes of methods those are used. Okay. The first such method is the collocation method. Collocation method implies that, look, let's say I have the domain like this, and then I have discrete nodes like this, and I decide to satisfy this differential equation at discrete points. Those points are called the collocation points. So, for example, I could choose a point here. I could say that this is where I want to set the residue exactly equal to 0. That means what? I am actually performing a integration of the weight function with the solution residue, but the weight function itself is a delta function, right. So, that is non-zero at xj, and everywhere else it is 0. So, that is the essential idea of collocation method, and you can very clearly see this is what you did, we did for finite difference method, right. Is not that what we did? We looked at the differential equation in a discrete form, that is what we call as a difference equation, and we equated them as those nodes, at the finite difference nodes. So, that is equivalent to your collocation method, right. So, that is what we did. However, we could also do something slightly different, and which we did not have time to do, is we could divide these domains into smaller subdomains, like what I indicated here. If I divide there and I decide to set wj equal to 1 in that particular subdomain omega j, and everywhere else it is 0, that means what? I am integrating the residue in that subdomain, right, instead of doing it over the whole integral. Recall that is what we have defined. So, if I talk about this, so this would imply that I am doing wj times r equivalent, and this I am doing it over the whole domain. Now, in the subdomain method, I will just do it only over that particular subdomain there. Then what does it mean? That I am in a sense putting wj equal to 0 everywhere else except that particular subdomain, and that is what we have given here in equation 1. Now, this method is what is called as a finite volume method. Okay. So, you can see the connection of the FEM with the different methods, like as I told you, your FDM would be more like your collocation method, FVM, the finite volume method, would be more like your subdomain method. Okay. Now, this particular method is also called method of integral relations, and one of the interesting aspect of it is the following, that you see, whenever we develop a new subject, we do not start always from scratch, we start with what exists before. For example, when we try to, let us say, solve computationally problem, what we do in FDM, we actually start off with a differential equation. What does it actually tell you? That it gives you a conservation principles as applied to a single small infinitesimal element. That is your differential equation, with the element size vanishing, right. However, when you go to compute, it is not that you are doing in an infinitesimal element, you are doing with a finite size element or domain or whatever you call it. Then what happens? Why should we then take this circuitous route? First derive a differential equation and then again approximate it over a domain, and then we satisfy that equation in an integrated sense over a finite domain. So, in finite volume method, what is done is this first part is eliminated. What you do is you try to satisfy those conservation principles in those finite domains itself, or finite volumes. That is why it is called finite volume method. So, what you do is you identify a small element or a small volume and then apply your conservation principle directly to that finite volume or finite element. That is not the same as starting off from a point and then integrating over a domain, right. I do not know if you appreciate that fact, but this is of prime importance, that we appreciate what we are doing. It's not just a simple, I would say, splitting terms just for the sake of it, but this relates to quite a significant difference in the different methods that we get. Okay, so now we can see under the umbrella of weighted residual method, we can classify FDM or FVM also as a subcase. Okay. Now, in each of these two methods that we just now talked about, you still are trying to get the residue equal to 0 either in a particular point or over a subdomain, right. That is what the name suggests, whether you are doing collocation or you are doing integral method of integral relation, you are still trying to put the residue equal to 0 exactly at some of those points. However, you just do not want to do that, because you are aware that it is very difficult to make the residue exactly equal to 0. What you could do is you could accept that there would be some residue, but let us try to minimize that residue. One of the way is minimize the residue in a least square sense. So, what I am going to do is I will define a functional which I am calling it I of c. This is some kind of a vector which is defined in terms of those coefficients, right, in your approximating solutions. Then what you are saying that I will choose this C1 to Cn in such a way this I of c is minimum. Okay. So, if I do that, what I would need to do is I will just simply differentiate the objective function or the functional I with respect to each of the Cj's, and that would actually give me this, because your function was r square. So, when I differentiate it with respect to Cj, I will get 2 R equivalent times the partial of that R equivalent equation with respect to Cj integrated over the full domain, and that is equated to 0. So, of course, you can very clearly see from equation 14, if you look at this quantity, this partial itself is nothing but your weight functions. So, this actually gives you some kind of a basis for choosing the weight functions. You choose it in such a way in this method, so that your residue is minimized in a least square sense. Now, this is one way of doing it. One of the oldest and the classical method is due to Bubnov and Galerkin. This is one of the best known methods, and it has a few variants also. We will talk about them. In Bubnov-Galerkin method, you choose these weight functions as the basis functions themselves. Okay. So, if you recall what we did, we wrote the trial function as this. Well, so, what we are saying now that these are what are called as the basis functions. So, in the Bubnov-Galerkin method, we choose the weights themselves as the basis functions. So, Wj's are nothing but Uj's themselves. Okay. Now, if you try to relate this Galerkin method, you can see the necessity for choosing a complete set for this basis function. Why? Because you are trying to obtain a trial solution which could be very arbitrary, and if I am trying to show it as a linear combination of a set of functions, it is quite expected that I try to take it as a complete basis functions, like what you do in your Fourier series or Legendre polynomial or Bessel functions. You are familiar with some of those complete sets. Okay. And then what you do is you automatically satisfy what is called as a uniform convergence, because we know that in the limit n going to infinity, I can define any function that we can talk about, and that is the whole idea of this. However, you can see that some of those complete sets of functions that we just now talked about, they happen to be global functions, right? Like if I take Fourier series, sine, cosine functions, they are global functions. You take Legendre's polynomial or Chebyshev functions, all those are global functions. So they are good, but they are global methods. We are not going to talk about those global methods. So we'll have to probably not worry too much about this uniform convergence at this point in time, because we have decided that we will choose these basis functions which has to be local in nature. That gives us some mathematical simplifications, okay, and operational ease. Okay. There is this other class of method as opposed to Bubnov-Galerkin. There is this Petrov-Galerkin method. You notice that all these mathematicians are from Russia, right? They have developed this subject long before computers came into being. They were ready with the method. So Petrov took Galerkin's method and he said, look, I mean, let's choose this weight functions as some other complete set of functions. It's not necessarily have to be those basis functions that we have chosen in approximating the solution. So that's what 17 says, that Wj is not necessarily of Uj. That could be psi of j, and the psi of j could be a complete set of functions, right? Because your intention is that you are going to take some kind of a local approximation to the basis, whereas you are trying to satisfy the solution residue in some sense, while being able to have a solution process which is as general as possible. So let's not restrict those Wj's as those local polynomials. Let's instead pick them up from a complete set of functions. That's what equation 17 suggests. This was actually necessitated by the observation that many a times one finds that this Galerkin formulation suffer from numerical instabilities. So this has been one of the major issue that up to 60s and 70s people are focusing their attention in developing Galerkin methods, but then that Bubnov-Galerkin variety, and people have experienced difficulties time and again, and this has to do with the numerical instabilities that we talked about, and they decided that we will choose instead not the Bubnov-Galerkin method, but Petrov-Galerkin method, and we will exercise our choice of the weight function in such a way that numerical instabilities can be circumvented. For example, this method called flow condition based interpolation method, FCBI, or let us say this streamwise upwind Petrov-Galerkin method due to Hughes in, so Professor Bathe is in MIT and Hughes is from Stanford. So they essentially tried to use Petrov-Galerkin method with the idea that we have seen that if we do not satisfy the physical principle, that's when we get numerical instabilities, right? While discussing about the property of compact schemes, we noted, like, if the information is propagating from say left to right and my closure is such that it is going from right to left, that violates the physical principle and that leads to numerical instability. So this is essentially the same idea with just different acronym that has been stated here. It's called flow condition based interpolation method. So like in a fluid flow problem, if the flow is going in particular direction, I will choose my basic, I mean this weight functions in such a way that is dependent upon the flow condition. So that's what it is. It is claimed by Professor Bathe and his group that it does preserve conservation of mass and momentum very accurately in flow problems. Okay. What is done here? Of course, the weights are chosen as step functions or Heaviside functions. So if I have a domain like this, and if this is a cell, I have a subdomain like this, and let us say the flow is going like this. So there is a distinct bias of the solution. Then what is suggested in this FCBI is that you take the weights, which would be like a step function, so that this is not going to affect this, but this element can affect the downstream element. This is like what we talked about our boundary layer solution. If you recall, in the very beginning we talked about the boundary layer solution. We say that if boundary layer develops, well, not necessarily fluid dynamic kind, but the boundary layer of any equations, there we could see that a shear layer kind of boundary layer forms, which has a directionality. That means the solution only any point affects the point downstream, but not upstream. So this is what is suggested, that you get that property through this Heaviside function or the unit step function. And the space time dependence, the space dependence of the solution is obtained from one dimensional convection diffusion equation that we have ourselves investigated. Yeah. So that is one way of doing it. However, we must be cautious about doing this kind of essential ideas are nothing but similar to what we call as the upwinding methods, right. That is what we did even in finite difference. You recall that we said that if the physics of the problem is such that this is the way it goes like this, then we do not try to do a central difference, we try to do a one-sided difference, because the information propagates in this direction. That is what we have seen, even that a first order accurate method in solving the convection equation turns out to be the most accurate method. We recall that 1D convection equation, we saw that first order upwind solution gives better solutions because it supports the physical principle. However, if you do not do it carefully enough, then we have also seen that there could be excessive dissipation coming into picture. In fact, this upwinding methods can introduce very large error, and this is one of the issue with this SUPG method that is used by a large number of people. They can produce engineering solutions, but as far as producing very accurate scientific solutions are still not in their domain. Okay. Now, when we go to finite element approximation and discretization, we basically, as we said, we take a trial solution of this kind, and then what we need to do is that we subdivide the domain to smaller elements. That is what we are talking about here. So if I talk about a particular element here, this is the element is defined, let us say, by the nodes here E, and let us say this is E plus 1. So this is your domain element E. Let us erase this part now. Now what we are going to do is basically in this element level itself will show the approximate solution would be dependent on where the element is and what is this element size is. Okay. We have mentioned that FEM and FVM are favored because you have complete flexibility in choosing that H size. Okay. So that is why that spacing between the two successive nodes or the width of the element is what is we are calling as H, right. So what we find that we can write that element level solutions in terms of the node values. So what has happened, let us say if I am plotting U, so I have the solution like this. So what happens is at this node I have these values, okay, and those values are given here. Those values are given here, uj superscript E. What is this function? This is what we are going to prescribe as dependence. Most of the time they are taken as a low order polynomial, either it could be a linear basis functions or quadratic or in spectral element method you can take a little higher order dependence, but this path is what you prescribe, and this is the solution that you are trying to pick up. Okay, that is what you are trying to compute. So they are your what we call there as uj of E. That this will be uj plus 1 of E. Okay, so and so. So this is what is being said, that uj's are the values of the solution at the nodes, and these are the usually low order approximating functions and which have a restricted footprint. What do you mean by restricted footprint? See, if I define a local expansion of phi j of E like this, so it means what? It is 0 outside this element everywhere on either side, and it is non-zero only inside. That is what we mean by local approximation. So that is what we are saying also, that restricted footprint of the basis function, that phi j of E. Now this you can now really see that uj plays this role here. uj is nothing but cj of T. That is what we have written there. Okay. So that is how we go about, and continuity of the solution u of x across element is ensured the moment I say that uj of E are nothing but the solutions there itself. So for this element this value is there, for the predecessor also I take that value. So there is no discontinuity at that node point. That is what is talked about in here, that we have the continuity of the solution, and that is ensured by picking up the nodal values as uj. Okay, and then of course we need to put some additional constraint on this basis functions that we will see case by case. Now these nodal values themselves could be time dependent. That is what we said, like uj of E could be like cj of T, right. So then when I plug this kind of expansion into the differential equation and then do this weighted residual method, I end up getting a ODE for uj of E as a function of time, and we need to solve that. Okay, so that's what it is. And since we choose these elements like this, and when I calculate the residue with the help of this kind of basis function, so then what will happen is we are going to see that this nodal functions that we are looking at here, because of this low order of phi of E, are going to be like what we have seen already in say FDM. It will involve only fewer neighbors on either side, right. That is the whole idea, that once we do that, we are going to get a sort of a discrete equation, and that discrete equation would involve only fewer points, right, fewer points. And then we are going to do that process for all the elements. Then we will have a coupled set of equations. We solve those equations as a ODE, and then we get the amplitude functions. And since this is already prescribed, you have already you are now obtaining this, so you get your solution. That is essential, is the whole idea. Okay. So elements are basically related in terms of their neighborliness. You would not see one element is coupled to another element which is far distant, right. So they are contiguous, they are neighbors of each other. Okay. So what do we do about this uj of x? That is what we are talking about. Uj of x, or what we talked about is phi j of E of x. We do take them as algebraic polynomials, and based on their order we can actually identify additional node points in defining this phi j of E. Well, this may seem little abstract now, but when we go and pick up specific examples, we will be able to understand. Okay. So whenever actually we satisfy the equation residue in an approximate manner. This is what is called as a weak form of the solution, right. Whereas, if you look at finite difference method, what we do there? We satisfy the differential equation so called exactly at some distinct nodes. Whereas, in finite volume or finite element method, we try to satisfy the differential equation in an integral sense over a finite volume or a finite element. So, whenever you do that, that is called a weak form of the solution. Okay, that is what we are talking about. So, whenever we adopt this weak form, then we are satisfying the differential equation in approximate form, and if there are any derivative boundary conditions, those are satisfied. That is the way we choose those phi j of p, etc. Okay. Whereas, if you have some Dirichlet type of boundary condition at the end of the elements, they have to be specifically satisfied by the approximate solution. They do not come out by the nature of the choice of approximate solutions. And we need to establish that these approximate solutions show solution convergence, and they are able to represent any kinds of solutions that you may expect to get. So, one of the thing is to show the convergence of the solution, this approximate solution must be continuous and differentiable in the weak form also. You understand that the essential difference in strong form versus this weak form is, in the strong form, whatever may be the order of derivative in the differential equation, you expect that out of your approximate solution. You satisfy the differential equation at discrete nodes, and you expect all those derivatives exist. Whereas, in finite element or finite volume method, when you actually integrate it, you are actually reducing the order of the system, right. So, weak forms are, that is why called weak forms. They are weaker in ensuring the convergence of the solution. So, suppose I have a equation with say second derivative term present. So, in a differential equation form and a strong form, I expect this approximate solution to be at least have second derivatives continuous in the whole domain. Whereas, in the weak form, if I integrate over the thing, I would actually reduce this requirement by at least 1, because I am integrating over the domain, right. So, if there are second derivatives and I am integrating it over subdomain, I am actually removing one order of the derivative. I come down to a lower order. Okay. So, this is what we are saying, that okay, we for convergence approximate solution still must be continuous and differentiable in the weak form, but this requirement is somewhat lesser requirement, less restrictive as compared to the strong form. The algebraic polynomial that we choose to approximate the function must be complete. What do we mean by must be complete? Suppose here I showed that in this element I take the basis function which is linear, right. Does it mean that it will not allow you to satisfy a solution which is constant? That would be dangerous, right. That would be dangerous. Even though I am talking about it's a linear variation in x, I still should be able to compute a solution where at the element level the solution may be continuous. That is what it means, that it must be complete. So, whatever may be the order, I may decide to take it say a cubic polynomial here, that would still give us the flexibility to satisfy any functional variation which could be maybe a constant, which could be linear or a quadratic, but it would surely be able to do that. If it does not, then we are in all kinds of trouble. Okay. So, this is what we must ensure, that our approximate solutions must be complete. It must include all lower order terms up to the highest order representation that we have used. So, let us now come to a very simple example. It is simple, but we will focus not only on this linear, we will also take a look at quadratic polynomials, where we define this space dependence of this function at the element level by a linear polynomial. Okay. So, what you need to do in this equation 19 then basically we will be looking for this constant C1 and C2. If we can obtain this constant, then we know what it is going to be. So, the local representation of the solution is as given here. Let us say I identify the E element spanned by this point E and E plus 1. So, the left hand point let me call it as 1, the right hand side point let me call that 2. So, basically then what we are talking about, that we try to find this constant C1 and C2 by fixing those values at those point 1 and 2. Let us say U1 and U2 are given, and you know the coordinates of this nodes E and E plus 1 as xa and xb, then it remains to be found how we can get this value of C1 and C2, and this is exactly like what we talked about as those nodal values, right. So, this C1 and C2 would be that. Please note that we choose this function UE of h in such a way that at this node and at that node they are always 1. Okay. The scaling factor comes from this, as we will see in the next slide itself. The scaling would come from here. So, what we are going to do is we are going to show this at the element level, the solution would be written like the space dependent part times the functional value at those nodes. Okay. So, this psi j of E is they are basically 2 in number, because that is what we saw, C1 and C2 are there. So, you are going to see the UE of h would be a combination of 2 linear functions, which is given here as psi 1 of E and psi 2 of E, right. So, one would start from this point. So, this is, if I call it as E and this as E plus 1. So, what I am doing, I am fixing origin, let us say x equal to 0 here. So, I just see that this psi 1 of E and psi 2 of E are such that at x equal to xa, psi 1 of E is equal to 1, and at x equal to xb, psi 2 of E is equal to 1, and that is what I have shown here. It starts off from 1, goes to the 0 in the other end, and the other way it starts off from 0 and goes to 1. That is what these two functions are, 22. So, basically if when you take a look at these approximate functions that we have chosen, they really work like a Dirac delta function, because at the node where you are talking about, that is where they take the value 1, everywhere else they are 0, right. So, this is the property that we are doing node wise, but at the same time in between the nodes we are saying it is actually not like Dirac function, but it is a linear function. Oh, okay. So, we will stop here and we will wrap it up, and there are a little bit of discussions needed about interpolation. We will do that.